So our next topic is covariance of two variables. Okay, covariance of two variables. The topic name is covariance of two variables. Let capital X and capital Y be two random variables. Then covariance of capital X and capital Y is defined as, you have to memorize this thing. COV, we use this notation, X comma Y, that is equal to expectation of, okay, capital X minus X bar. Capital X minus X bar means the mean. We have already know this thing, okay? First center moment, second center moment, we have already covered in the couple of videos back yesterday. So cov xy is equal to expectation of x minus X bar, okay, where X bar is the mean of this random variable capital X multiplied by Y minus Y bar, okay? Where X bar and Y bar are the mean of X and Y respectively. In practice, we use the following results on covariance. So, we will have, so first we have to memorize what is the definition of covariance. Cov xy is equal to expectation of, first we do the product of these two, x minus X bar and Y minus Y bar, then find out the expectation of the result. That gives you the covariance of X and Y. Now, we have some theorems on covariance, okay. We will be just studying the theorems. So, theorem 1 says that cov x comma y, that is equal to E xy minus ex dot ey. Okay, page number 142. We are in page number 142. Already said at the beginning of the video, cov x comma y, that is equal to E xy. Okay, joint means first type E xy. Okay, then dot, sorry, E xy, then minus ex dot ey. So this is the covariance of x and y. This is theorem number 1. Then we have theorem number 2. If x and y are independent random variables. So theorem number 1 and theorem number 2, there is a difference. In theorem number 2, x and y has to be independent. Okay, in theorem number 2, it is mandatory for x and y to become independent. Okay, only then theorem number 2 is applicable, otherwise not. I repeat myself. In theorem number 2, it is mandatory for x and y to be independent, otherwise theorem number 2 is not applicable. If x and y are independent random variable, then their covariance is 0. Remember this thing, okay? Again, I say, if x and y are independent random variable, then covariance is 0. Because cov x comma y, that is equal to what? Formula states exy minus ex dot ey. Now, if x and y are random variables, then we can write this thing as ex dot ey minus ex dot ey. These two terms get cancelled out, so we will have 0. So if x and y are random variables, suppose xy will become equal to 0. Okay. So that we have finished the theorems, two theorems on covariance. Next, we will go to correlation coefficient between two variables. Next topic. Okay. Page number 143. Page number 143. Correlation coefficient between two variables, between two random variables. I am not writing down the subtopic name, okay. We are not going to study the example, it is not required, okay. We are unnecessarily then otherwise delaying. The correlation coefficient between two random variables x and y is defined as rho xy, that is equal to cov x comma y divided by rho divided by, this is standard deviation, sigma x and sigma y. This is the correlation coefficient. The correlation coefficient between two random variables capital X and capital Y is defined as rho xy, that is equal to cov x comma y divided by sigma x dot sigma y. Where sigma x is equal to, sigma x is standard deviation, it is nothing but the square root of, positive square root of variance. We have already studied yesterday how to find out the variance. Please, those who have not attended, please look in the videos of variance, okay. So what it is says, so where sigma x and sigma y are the standard deviation of x and y respectively. Standard deviation means positive square root of variance. Okay. The degree of association or the strength of relationship between x and y are measured by correlation coefficient. If the probability of assuming data of x are not affected by those of y, then we will get rho xy is equal to 0. That means if these x and y are independent variables, then we will get rho xy is equal to 0. Okay. So what is correlation coefficient? Already now we have studied. Now there is nothing else. If necessary, then we will again cover some topics later if it is required for pattern recognition. Till now, I don't think that you need other things from this chapter. Let's now go to page number 195. Okay, continuous probability distribution. So this will be our next topic now. Continuous probability distribution. Go to page number 195. I've already posted the images in your WhatsApp group. Go to that. So we have studied covariance, we have studied correlation coefficient. Okay, please make a note of these things in your copies, and if necessary, you can study them from other websites or books also. Not necessary that you are bound to follow me, but still, I am doing these videos only for your convenience. Okay. So you can now page number 195. You can read the introduction yourself. So what is probability density function? Let's go on to page 6.2 introduction. You can read it. Why is probability density function used? All these things you can also read by yourself. Now let's go to the mathematical part. So probability density function or density function and continuous distribution. Okay. So probability density function is also called as density function. Let capital X be a continuous random variable. Continuous random variable, I've already shown you that if there is a limit, discrete random variables means that it can only assume specific values. The values of capital X can only assume some specific values, not all. But in case of continuous random variable, what it was, there was a range and the values of X can assume all the values in that range. Okay, this was the difference between discrete and continuous, already explained in the first videos. Let capital X be a continuous random variable with distribution function. So let us write down the distribution function of capital X. Okay. So the subtopic name is probability density function, isn't it? So let me write down. Or you can also call it as density function. So let capital X be a continuous random variable with a distribution function. Just in the last video we have studied what is a distribution function. So capital Fx, that is equal to P capital X greater than minus infinity less than equal to small x. Okay. Then a function small fx is said to be probability density function PDF of capital F if fx is integrable on the interval a comma x for all a. Okay. So we can call that small fx is the probability density function. This is the distribution function. This is not the density function. Okay. I repeat myself. This is the distribution function. Already this thing I've covered in the last lecture, I hope. Okay. So this is distribution function. Now we look for another function. This is small fx. Okay. This will be called as the probability density function. This will be called, I repeat myself, this will be called as the probability density function only if it holds some condition. What is the condition? If fx is integrable on the interval, let us assume an interval a comma x, okay, closed interval, for all values of a. And if, see, fx is equal to minus infinity x, okay, ft dt. Only in such a case, this ft function or fx function can be called as the probability density function. Okay. So this is the distribution function and I choose another function fx, ft, whatever it is. This fx will be called as the probability density function in this interval a comma x for all values of a. If this condition is satisfied, fx is equal to integration of minus infinity to, this is minus infinity, okay, minus infinity to small x. Now the interval is from a to x, okay, ft dt. This holds for every real value of small x. Okay. Now let's study some fundamental properties of PDF. Fundamental properties of probability density function. Let's study them. Study, we have moved out from that. Now, what are the fundamental properties? Property number 1. If fx is a PDF of a random variable capital X. Guys, are you looking in page number 195? I am repeatedly telling you, go through page number 195. It's posted in the WhatsApp group as an image. If you are not able to see that page, please download them again, because because you don't have this book, so unless and until you follow those pages, you will not be able to understand a bit. Okay. If fx is a PDF of a random variable capital X, then the first property 1 is fx is greater than equal to 0. Okay, this is the first condition of this is the first property of probability density function. And the second property is minus infinity plus infinity. Okay, fx dx is equal to 1. We have to remember these two properties. So if fx is the probability density function, okay, just now how it becomes probability density function, I've just shown you in the last couple of minutes back. So fx is equal, we have now known what is probability density function. Now we will study two properties of probability density function. The first property is the value of fx is always greater than equal to 0, and the second property is if you make integration of fx, the range between minus infinity to plus infinity, we will have fx dx is always equal to 1. Proofs you don't need. Okay. Now let's go to the second property. Means this was property number 1, then two sub properties. You can also name them as A and B. Now we go to the second property, that is, the second property says since f over of infinity is equal to 1, we will have integration of minus infinity to plus infinity ft dt that is equal to f infinity that is equal to 1. So this was capital F was actually nothing, but actually it was the distribution function. Distribution, you know very well, the distribution function over infinity is always equal to 1. Distribution function of infinity, that is always equal to 1. So if f infinity is equal to 1, we will have minus infinity plus infinity ft dt that is equal to f infinity that is also equal to 1. So this will also become equal to 1. Next again, this limit you don't need right now, but still just let's make a discussion on that. Further properties of PDF are number 1, as fx is a continuous function, please go to page number 196. Please go to page number 196. Okay, you can skip out property number 1 over there. See guys, I'm explaining you that this is not a maths class, so only those properties which I feel is necessary for your this pattern recognition class, I'm only discussing those properties. Remaining properties, if you find any interest, you can go to any statistics class and learn from there. Okay. So the properties of PDF. So property number 2, for a continuous distribution, you know what is continuous distribution now. Property number 2. Okay. So this is P capital X is greater than equal to A less than equal to B. That is equal to P capital X greater than A less than B. That is equal to P capital X greater than A less than equal to B. That is equal to P capital X greater than equal to A less than B. That is equal to integration of limits between AB ft dt that is equal to capital FB minus capital FA. Okay, you have to memorize this thing. For a continuous distribution, P capital X lying between means P capital X greater than equal to A less than, memorize this thing, okay? Capital X greater than equal to A less than equal to P, that is equal to P capital X, this is capital X, only greater than A and less than B, that is equal to P capital X greater than equal to A less than B, that is equal to P capital X greater than equal to A less than B, that is equal to integration of AB ft dt, that is equal to FB minus FA, where F is the probability density function. Again, next theorem, next property. If fx is continuous, then we must have fx is equal to differentiation, okay? F dash x, differentiation of this distribution function. Fx, if fx is continuous, then we will have fx is equal to f dash x. Now, the last property, that is property number 4, we will have in differentiation notation, page number 196, I am reading from there. In differential notation, we will have P x greater than capital X less than equal to x plus dx, that is equal to f x plus dx minus fx, that is equal to d fx, that is equal to f dash x dx, that is equal to fx dx. Please follow this as sequence wise. So we have P capital X is greater than small x and less than x plus dx, okay? D means, you know, very small amount, okay? Or differentiation of x, that is equal to fx plus dx minus fx, that is equal to what it is? D over of fx plus dx minus fx means very small difference. So d over of fx, that is equal to, if you do differentiation, you will get f dash x dx, that is again equal to fx dx, okay? So this closes temporarily the properties of PDF, probability density function. We may again revisit them later as per our requirements in pattern recognition class. But for now, bias decision surfaces and other things, this up to this knowledge is enough, more than enough actually. Now we will study some properties on, again, expectation or mean of a continuous random variable from page 197. Okay. We will not go into any more illustrations. It's making videos longer and longer. So we will just go for examples. This I will cover again in the next video.